We are going to start Chapter 3, Section 3.1 with a really important rule. So this video is going to be about the chain rule, and there's going to be certainly another one after this, so we're just going to start it here in this video. So what we're looking at is what is going to be the derivative of a composition evaluated at some specified point here. So let's start off and try to motivate this a little bit here first. So suppose I have some function, so let's just let h of x be this composition here, g of f of x. And suppose that I want to find what is h prime, so the derivative of this composition function, evaluated at a specified point. So suppose I want to figure out what is h prime of a. Okay, well, using our definition of the derivative at a specified point, here's what we would know. We would know that this would equal the limit as x approaches a, so this was that first definition of the derivative we talked about, of the original function g of f of x minus g of f of a, and then all divided by x minus a. Now, what we are going to do here is we are going to multiply by a version of 1, so that's going to keep it legal, right? I'm going to have us multiply by f of x minus f of a all over itself. F of x minus f of a. All right, so when we do that, what are we going to have here? So first, just recopy here my limit as x approaches a. And all I'm really going to do here, since I am multiplying two fractions, the product is the product of the numerators over the product of the denominators. And what that allows me to do is I'm going to leave the numerator here exactly the same. And I'm even going to leave this second numerator the same. But what I am going to do is I'm going to change the two denominators. Okay, so I'm going to make this denominator f of x minus f of a, and I'm going to make this denominator x minus a. And that's okay, because multiplying two fractions, I just multiply numerators, multiply denominators, and multiplication is commutative. All right, well, we now also know that with limits, a property of limits is we can take a limit of a product as the product of the limits. And so that's what I'm going to write out here. So I'm going to take the limit of that first fraction, if you will, and then times multiplied by the limit as x approaches a of the second, f of x minus f of a over x minus a. All right, well, hopefully, at least the second one should look really familiar, because that is the exact form in that second fraction of f prime at a. So this is your definition, that first limit definition that we learned. So our first limit definition for f prime at a. Now, the first one is also the first type of limit definition that we learned, but this one, of course, looks a little bit more awkward because it is a composition that we're working with here. So it's the limit as x approaches a. The original function is g of f of x, and then minus that function with a, g of f of a. And then if you kind of treat the inside, instead of it just being an x, it's an f of x. So then in the denominator, we have f of x minus f of a. So that is going to be our notation for that is g prime but it's not just g prime at a, it's g prime at f of a. So this is g prime of f of a. So like notice in the second one where there was an a, because that was f prime of a, here there is an f of a. And in every other location that there should be, like normally up here there's just an a, and here that's where I have my f of a. And then over in the first terms, every place where normally there would just be the x, in this case there is the appropriate f of x. So here's what we now have. So just a little justification there for what is this really important chain rule, which is going to say, in general, for any x, the derivative of g of f of x is going to be g prime of f of x times f prime of x. And so this first g prime of f of x, this first factor, this is really saying in words, which a lot of times will be phrasing, so that's important. This is the derivative of the outside function. So this is the derivative of the outside function, and then kind of key here with the inside function left alone. So we haven't done anything at that point with that inside function. So g prime of f of x is the derivative of the outside with the inside left alone, and then multiply that by f prime, and of course this is just the derivative of the inside function. So this is the derivative of the inside function. And that's the chain rule. You might also see it written with Leibniz notation. And with the Leibniz notation, it looks like dy dx is equal to dy du times du dx. And in this situation, y is your outermost function, and then u is your inside function, where u is a function of x. So you might see it written, so I'll say here, where u is equal to, some function of x, where, so this is your inside function. Okay, so that's kind of what you have there. All right, so what is this going to look like more in practice? Okay, that's what we want to write out here. So when we're talking about the chain rule for powers, this is going to be a really important one. When we talk about powers, those would obviously include radicals. So we can, of course, rewrite any of our radicals with rational exponents. All right, so what is this going to look like then? Okay, so this is going to say if you're taking the derivative with respect to x of some inside function, f of x, raised to some outer power n, the derivative of the outside would be the power rule. So n with the inside function f of x left alone raised to the n minus 1 power, and then times the derivative of the inside, so times f prime of x. So that's what it would look like for powers. For the exponential function, whatever is up in that exponent, that is the inside of an exponential function. So if that is more than just an x, you need to think of chain rule. So derivative of the outside would be e to that with the inside function left alone, f of x, and then times the derivative of the inside, so times f prime of x. All right, then the trig functions, I think honestly the trig functions, their insides are a little more obvious. They actually look like what is inside of that trig function. So with these, and I'm not going to list them all out, but I just want you to get the feel for it. So if you had, the derivative of sine of some inside function that's more than just an x, then you would say, okay, the derivative of sine is going to be cosine of that inside function left alone, f of x, and then times the derivative of the inside. Okay, and that's, the type of thing that would continue here. Let's say we get down to derivative with respect to x of, I'll write out a few of them. Let's say tangent of f of x. So the derivative of tangent would be secant squared of, again, inside function left alone, f of x times f prime of x. And then again, kind of continuing, this is the same idea for all of these, and then maybe getting down to the last one, derivative of cosecant of f of x. And so derivative of cosecant is the opposite of cosecant of inside left alone f of x, cotangent of inside function left alone f of x. So that whole thing represents the derivative of the outside with the inside left alone, and then times the derivative of the inside. So this is how quotient rule is going to really manifest itself right now. Chain rule, I think I just said quotient. This is how, chain rule is really going to manifest itself right now. All right, so we're going to start with an example where we can show, we're going to do one example to kind of end this video, and we're going to show it two ways so you can kind of get a side-by-side comparison. So let's look at an example of, let's let y equal 2 over x squared minus 2. And I want us to find f prime of x with, and then we're going to do this two different ways. So part A, let's first just do it with how you would have done it before today, which is still perfectly fine, by the way, for a problem like this one. Let's look at it with quotient rule. So with quotient rule, that's a familiar hat, hopefully. So f prime would be, start with our denominator left alone, times derivative of numerator, which in this case is 0, minus numerator left alone, which is 2, times derivative of denominator, which is 2x, all over our denominator quantity squared. So this is going to tell me that my f prime is negative 4x over x squared minus 2 quantity squared. Okay, so that should look familiar. All right, now I'm going to have us kind of slightly rewrite this function and think of it from a different approach, and we're going to do it this time using chain rule. All right, well, left like it is, it's definitely a quotient rule problem. But if I rewrite the original by bringing up the entire denominator and thinking of that entire denominator as raised to the -1 power. Now, incidentally, I would only ever potentially even make the choice to do this if the numerator is a constant, because otherwise I would just be turning a quotient rule into a product rule, and I don't really save a lot by doing that. In this case, it might be a smidge easier to think of it this way once you catch on to chain rule, but honestly, both methods here are relatively the same in terms of, the work here. All right, so what we now have, so here's our classic, kind of scrolling up here, example of an inside function raised to an outer power. So I want us to be thinking of it exactly that way. So this whole x squared minus 2, this is our inside function in this case. So what we have is we have 2 times an inside function raised to the -1 power. So if we think about using the chain rule is going to say, so I'll just say dy dx here. All right, that we are going to have, bringing down our -1, that's going to be -2. And again, inside function is going to be left alone. Now, I am not going to typically always write this out. I'm just going to do this like initially. And the inside function is going to be left alone, and then raised to the -1 minus 1 would be the -2. And then we're going to multiply this by the derivative of the inside. So kind of compare that to what we have up above with the at the very top of your screen there. That's what the power rule looks like with chain rule. All right, so what do I really have in this case? Let's make these substitutions in here. The f of x is itself an x squared minus 2. So I really would have had this -2 times x squared minus 2 raised to the -2 power, and then times the derivative of the inside here is, of course, 2x. So if I realize this is all one term here, really, because it's all multiplication of factors, I can then put this kind of all together. I can multiply the monomials. -2 times 2x is -4x. And then if I want to slide that quantity to the -2nd power into the denominator where it's to the +2nd power, well, we now have our derivative. And as I'm looking at this, I got a little bit sloppy with my notation in part A. I never really caught that here. So in this case, I shouldn't call it y and then say find f prime. That's bad. So let's just say find, since I used the dy dx notation here, I'll just say find dy dx, the derivative. So I shouldn't have used that here. So I just, of course, just for purposes of good notation, I need to go back and fix that. All right, so basically this is it on this video here. So we've seen an introduction to our chain rule. And so in so doing, we've now applied it just once in this one example. So next time we're going to come back and look at a lot of chain rule examples. Working with chain rules is a super important topic as we move forward here.